Hi students, from the CS 8351 Digital Principles and System Design under the Unit 1 Boolean Algebra and Logic Gates. Today we are going to discuss about arithmetic operation involved in different binary numbers and different kind of binary codes. This is Professor Ilangovan from CSE Department, NPR College of Engineering and Technology. We'll go into the subject, and in this session we are going to understand about different binary arithmetic operations involved in binary numbers. Well, we are going to do the binary arithmetic operation to simplify it, and how to do the complement, and with the help of how we are carrying out binary arithmetic understood. And of course, for the to handle the negative numbers, we are going to see numbers, and what are the different kind of binary codes available in the binary system or in the digital system. That's what the today's session. So once to do the addition, how we are doing the addition with the conventional decimal number understood with the known conventional thing. A similar pattern we are, so we look into the regular conventional decimal number addition. The method to numbers. We want to add numbers. After adding those two numbers, how we are writing it? What we are adding? Yes, the base result either it is greater than or equal to base. Let's see. 5 plus 5 is greater or equal to base. This is satisfied. Once if the result is, we have to subtract the base value from. So if you are doing that, you will get the, whenever you are subtracting base, you have to one in high order. So that one, if suppose there is another significant value similar to the 5 plus 5, what will happen? We have to add the carry with the, so now the result is going to be 11. So in the 11, I am comparing the base and we are subtracting the base, and result and remaining that is 1. If there is no number 1 0, it's similar figure. We are going to add that 2. So if you want to add two numbers, we have to add the 1 and 1. So 1 and 1. So the result is what? 2. That 2 we have to compare with the base. What is the base of the binary number? 2. So we have to subtract 2 in the with the summation 2. So 2 minus 2. We are comparing 2 minus 2. So we are getting result as 0. Whenever we are subtracting a base, we should have a carry to the next higher order level. So we brought into the 1 as a carry. Now you assume there is a 0 and 1 to be added. Now if there is a carry 1, so if you are adding these things 1 plus 0 plus 1, you will end up with the summation result as 2. So whenever you are getting the result, that has to be compared with the base value. Whenever the summation is greater than or equal to base, you have to subtract a base from that. So similar fashion, if you are doing so, now the result is 2. That is also greater than or equal to 0. So the result is 0, and we are forwarding the carry 1 to the higher order level. Now you assume that there is a 1 and 1. If you want to add 1 and 1 with the carry, so you will be getting 3. So from the 3, you have to subtract 2. So the result is 1. And of course, you have subtracted 1. So carry as 1. similar fashion, if you are adding 1 and 0 with the carry, you will be ending with result as 2. So, and there will be a 1 carry. And again there will be a 1. So result is 1 and carry is 1. And it goes on like this. So this is going to be the final result of the number what you have added. So for example, it is given as a 61 and 23 for that binary number we have had. So the result is also we are getting 84. So this is how we'll be doing the binary addition. And you recollect how we are doing the decimal subtraction. So in the decimal subtraction, we are using the method of borrowing from the higher order level when the subtrahend is greater than the minuend. So the similar concept we are going to apply in the binary subtraction also. Now there is two numbers, 1 and 1 we want to subtract. The minuend and subtrahend both are equal. So in this case there is no problem. So it's going to be 0. And here minuend and subtrahend, if we are comparing, subtrahend is greater, so we have to borrow. So what we are borrowing? We are borrowing the base value. You just recollect how we are subtracting 5 from 3. So what we are doing, if you want to subtract a 5 from 3, so 3 we will be making as a, we are borrowing 1 from the lower order. So that is while we are borrowing it coming as a base value 10. So 13 minus 5 we will be getting as minus 8 as answer. So similar fashion here we are borrowing. So from the higher order we will get 2 as the borrow. So we will be getting borrow as the 2. So from the 2 we have to subtract. So 2 plus 0 you will be getting 1 0. So from that 1 0 you are subtracting 1. So remainder is going to be 1, and there is no something else. And here you borrowed 1, so remaining you have only 0. Again you wanted to do 0 minus 1. So that 0 minus 1 means what? Again you are borrowing 2. So result is 1. So if there is 0 minus 0, you will get 0, and 0 minus 1 we are borrowing 2, and the 2 is carry forward over there, the resultant 0. So it goes on like this. So the final result is going to be like this. If you are doing subtraction 77 minus 23, you will end up with the result 54. This is how we are doing the binary subtraction. And similarly the binary multiplication. Here also you just recollect how we are doing the multiplication in the decimal numbers. So you will be taking the numerator and you are multiplying the multiplier. So each digit there you will be taking and you are doing the multiplication. And you will getting the partition, and finally you will be finding the total sum of all the things. So in similar way will be doing the multiplication. There is a number, if you want to multiply by 0, so and you are moving to the next digit. When you are moving to the next digit and you are multiplying that, and in summation you will be doing one bit left shift. That's what we are doing in the number 2. So this is how we will be doing the multiplication. So if there is a 1, we will be copying the multiplicand as it is. If there is a 0, we will be copying only 0. Finally, we are finding sum of all the things. So that is going to be the our answer. So this is how we will be doing the binary arithmetic operation. So this and all is the method of pen and papers. And what we have seen in the negative subtraction, during the subtraction, we came with the negative numbers to be represented. Say, if we want to subtract minus 1 or 1 minus 1, there we need to represent minus 1. So how to represent that negative numbers? So the negative numbers generally can be possible to represent in 3 ways. Either it can be represented by using 1's complement, 2's complement, and signed magnitude representation. These are all the 3 methods available. Before going into depth of the negative number representation, first we will get introduced about complements. how the complement is there, how we are getting the complement. Then we will try to understand with the help of complement how we are representing negative numbers, then how it is involved in the arithmetic process. So usually if you are taking the complement, generally the complement will be represented in two categories. One is base complement and diminished base or radix complement. Base complement and diminished base complement, or radix complement or radix minus, diminished radix complement. So the complement can be represented in two ways generally. Base or radix are same. So we can say radix complement or diminished radix complement. Or even it can be represented as, if base is n, complement n minus 1 complement. This is in general. So to the base only we are saying. Suppose if there is base is 10, then 10's complement, 9's complement. If the base is 8, 8's complement, 7's complement. If the base is 16, so 16's complement, 15's complement. If base is 2, then 2's complement and 1's complement. Getting this? So if you are saying a radix or base complement, it is what is the base. So with respect to, we are saying the complement. And another one is diminished radix complement. So from the base, we are reducing 1 and we are taking the complement. So that's what we are saying the example. If the base is 10, it has two type of complement. The radix complement is 10's complement. Diminished radix complement is, yes, diminished radix complement is 10 minus 1, 9's complement. Similarly, if you are coming to the binary values, its base is 2. So radix complement is 2's complement. Diminished radix complement is 2 minus 1. So 1, 1's complement. So if you are taking complements for binary numbers, there is 2's complement and 1's complements. So that's what is explained in this. So how to take the 9's complement, that is diminished radix complement. If the number base is 10, then the 9's complement is the diminished radix complement. So if a decimal number is given, how we are getting it, that is the next step. So what we are doing, usually if any number is given, for the number it has to be subtracted by, each position to be subtracted by 9. The example 546700 is the given. We want to take 9's complement. So each digit you subtract it from 9. So what will I subtract? 5 from 9, 4 from 9, 6 from 9, 7 from 9, 8 from 9, and another 0 from 9. Each digit to be subtracted 9. So you will end up with the answer 453299. So 546700 is a number. Its 9's complement is 453299. So you will understood later on how it is going to helpful, how it is a meaningful. In a similar fashion, if there is a number, that number, every number to be subtracted from 1. So each bit position to be subtracted from 1. For this, you take a number 1 0 1 1 0 0 0. So that is the number given. So how to get the 1's complement for that? So each bit position to be subtracted from the 1. So you will be getting 0 1 0 0 1 1 1. So that is the complement for the given number. So this is the straight mathematical approach to get 1's complement of any given binary number, each bit position to be subtracted from 1. So this is the straight method. But the conventionally how we can do is, if you want to find the ones complement of a number, you you take complement for each bit. That is complement in the sense you change ones as zeros, zeros as ones. You will get the ones complement of a given binary number. This is very conventional method. Everyone is going to do that because it is going to end up with the same result. You see that 1 minus 0 will get 1. The zeros complement 1. So we are getting 1 minus 0. So if the bit is 0, the result is 1. And you see the next one. If the number is 1, its complement 1 minus 1 equal to 0. So that's what, whenever if you want to take ones complement for any binary number, if there is a 1, you make it as a 0. If there is a 0, you make it as a 1. So that is equivalent for ones complement. So that's what diminished radix complement or ones complement. Change all zeros as ones and all ones as zeros. You will get the ones complement. So you see that example is given 1 0 1 1 0 0 0 0. So if you are converting all ones as 0 and zeros and ones, you will end up with 0 1 1 1 1 1. This is the ones complement for the given number. So now we will see that what is going to happen if you are adding the number with its own ones complement. You just check it out what's going to happen. You see that you will end up with all ones. Adding a number with its own one complement, the result is going to be, why? Because why it happened? Since binary numbers, how we are obtaining the complement? By subtracting from 1. If you are doing it, it is very obvious to end up with the same answer. So we will be ending up with result. So the next thing is radix complement, 2's complement. If you are taking the binary number, it is going to be the 2's complement. If it is a base number, then in the, if it is a 10, complement is called as 10's complement. Take a 10's complement number. Zero, 3, 9, 8. You will get see 144. The difference from nth complement to complement is it is be, so after taking the diminished complement, just you will get base complement in it in complement of a number. First you take the 9 complement, each digit to be subtracted from 9. Obtain the 9 complement. To add 1 with least significant digit, you will end up getting base complement. So here end up with, whether you are using 7 complement or 2 or 1 complement, the same. First to find the diminished radix complement, then add 1 with significant position, you will get base or radix complement. So that's what we are supposed to follow every time. And the similar to for the base 2 also. You, how to find the ones complement? You change all ones as ones, and finally you add 1 with the LSB, least significant bit. You will get 2's complement. So that's what. So ones complement of a number and take 1 with the LSB. So you will get the 2's complement of the number. So this is how the, that's what the definition is. Toggle all bits to the left of the first one from the right. This is the another approach. So how to convert this? So here you can see the given number is 10110000. So how to convert it into 2's complement? This is another shortcut method. So toggle all bits to the left of the first one. So you starting from leftmost, the first bit is 1 and 0, 1, 1, and after that 4 zeros are there. So if you want to the things, we start all the things from the right hand side of the numbers till the first one. So last 4 zeros we are adding as first one, nothing is in the first one. So that we are adding. So now you have 101. Now we change it as 010. That's it. So you will end up with the same answer. So to find 2's complement of a binary number, you can follow any one of the method which is convenient for you. The one method is take 1's complement for the given binary number and add 1 with LSB. Or else, starting from the right hand side, copy down all the bits as it is till reaching the first one. And copy down that one also as it is. And for the remaining numbers, you flip or you toggle ones as 0 or zeros as ones. That's how we can end up with the 2's complement number. Now the thing is how we are going to do the subtraction by using the complement, because that's our main aim. We got the complements, how to find. So we understood how to find the complement. Now the process is how we are supposed to doing the subtraction. That's our main goal. So here, if you want to do the subtraction m minus n, so there is no issues as long as the n is less than m. But the problem raises when n is greater than m. So that we are going to deal with this, how we are going to subtract the two numbers with an example. Now you see the two numbers. One number is 72532 minus 3250. So how we are going to do this? Now it's a 5-digit number. So for the next number also, we have to take the tens complement of the number. So for 3250, you assume that there is a leading 0 to make it as a compatible to the first one. So 9 minus 0, 9, 9 minus 3, 6, 9 minus 2, 7, 9 minus 5, 4, and 9 minus 0, 9. Now you add 1 with that. So you will get 96750. So that has been shown in the example, tens complement of n. Now we are not doing the subtraction because the number negative is included in the number itself. Now we are adding the 2. If you are adding the two numbers, you will get 169282. That is the sum we are getting. Now in that we will discard the carry. We will end up with the answer 69282. So that is, if you are subtracting 3250 from 7253, you will end up with 69282. So that is the conventional number. The similar fashion for another conventional number, we'll straight away move on to the another example to the binary numbers. So if you want to add two numbers, subtract two numbers, x minus y. So you have 1010100, and you assume the value of y, and its 2's complement is 01111101, and you add these two numbers, you will end up with 1001001, and there is a carry. In 2's complement, If carry comes, we will discard it and we will get the result as x minus y. And sometimes there won't be any carries generated. So that means the suprahand is greater than minute. So whenever it comes for the result, we have to take again 2's complement for that. So we can formulate the rule for the 2's complement subtraction. If we want to subtract a number, then we have to take complement for the suprahand and add with the minute. So here x is the minute and y is the suprahand, and take the complement for y, add with x, and you will get the result. After getting the result, check for the occurrence of carry. If the carry occurred, it is a it shows that the result is positive and discard the carry. And if there is no carry, it indicates that the result is negative, and take the 2's complement for the result to obtain the actual result. Now if you are coming to the 1's complement, here also similar to that. And if you want to do subtraction of x minus y, and x is minute and y is suprahand, take 1's complement for the suprahand, add with minute, and check for the carry. If there is a carry, the result is positive, and the carry to be added with the LSB. But in the previous case, we straight away discarded. But in 2's complement, in 1's complement, if carry is generated, that to be added with 1's complement again. Now that is going to be the result of x minus y. If there won't be any carry after doing x minus y, that is suprahand you are taking complement, adding with x. If that result is not generating a carry, means the result is negative, take the 1's complement for the result to obtain the original value. This is the complement. So this is the advantage of 1's complement and 2's complement numbers. One, you have not mentioned anywhere the minus. That minus comes into the complement, and we are doing always addition of the number, but it performing the subtraction. So that's what we are using the complement. And here if you are looking, 1's complement and 2's complement are doing the same, but there is a simple difference. In 2's complement, if there is a carry, we are simply discarding the carry. But in 1's complement, if there is a carry, we are doing addition one more time. So that's what in many of the systems, the 2's complement is preferred rather than 1's complement. But still, both complementing methods are used in different kind of discrete units, either in the whole system or in part of systems. The another representation of signed magnitude is by allocating the magnitude, whether the number is a negative or positive, the most significant bit location itself is reserved to represent sign. So if the bit value becomes 0, that indicates the whole number, whole value is the positive value. If the number is negative number, the MSB is going to represent it as 1 to show the entire number as the negative number. The advantage here is we are not taking any complement or nothing. We can do as it is simply. The system is simple. But the major disadvantage here is we are allocating one bit position for representing the sign itself. So the magnitude value what we are storing in that will get reduced to half of its maximum value. So you just look into that. If there is a 4-bit location to represent, we can enter the value maximum of 15, that is 16 values, 0 to 15. If the 4th bit is reserved for the sign value, remaining 3 bit alone we are able to mention the values. So if you are mentioning only the remaining 3 bits, the value is 0 to 7, that is 8 combination. It is just half of the previous value of 16. So that is the only disadvantage. But the so simplest thing is the magnitude become a 1 or 0, the system is going to so simple. So this is the representation of different numbers with its ones complement and twos complement and signed magnitudes. So if you are looking in the positive numbers, all signed, that is twos complement, ones complement and signed magnitude, all the three looks like same. So there is no problem in the positive numbers. But when you are going for the negative number only, you will be having the negative signs, different values for sign magnitudes. So this is how we'll be doing additions. So in this session, we discussed about the binary arithmetic operation performed in the binary numbers and how we are taking complements, radix complement, diminished radix complement, in case of binary, two's complement and one's complement, and signed binary numbers with the magnitude representation. Thank you, student. This is Professor Ilangovan signing off. We'll meet with the next topic in the next video. Thank you.